This article is titled Modeling of an 18 degrees of freedom humanoid robot using recursive analytical method. The objectives are: develop a recursive dynamic modeling method for an 18 degrees of freedom humanoid robot using a recursive method. Formulate recursive expressions for forward kinematics, differential kinematics, linear and angular velocity, and inertia matrix. Implement the position control based on hyperbolic tangent function. Validate the proposed modeling and control the strategy through MATLAB Simulink. We propose 4 open kinematic chains to describe the position and orientation of each link of the Violet Premium robot. Observe in Figure 2, an arbitrary point in space P is considered. P0 is the coordinate vector of point P with respect to reference frame sigma 0. Additionally, another reference frame sigma 1 is introduced, where P1 denotes the coordinate vector of point P with respect to sigma 1. The vector D represents the displacement of frame sigma 1 with respect to frame sigma 0. Furthermore, the rotation matrix of frame sigma 1 relative to frame sigma 0 is also considered. Methodology. The position of point P can be generally expressed by this equation, which is used to compute the recursive forward kinematics of each link of the robot. Using the properties of the skew-symmetric matrix S, the recursive differential kinematics can be computed. The following equation computes the linear velocity Jacobian, where the term T is the matrix that adds components to each column J of the Jacobian. This is the angular velocity Jacobian. These Jacobians are then used to compute the robot's inertia matrix. The next step is to obtain the Lagrangian of the robot. And finally, the equations of motion based on the Euler-Lagrange formulation are derived using this expression. The implementation of the controller based on the hyperbolic tangent function is proposed. This control law is defined by this equation. Results. The following section presents some simulation results. The desired joint positions shown in the table are proposed for the right leg. These plots show the behavior of the present position of each joint. These plots present the position errors for the right leg joints. The torques applied to the right leg joint are presented in the following plots. The conclusions are: the Euler analytical method proved effective for solving the dynamic modeling problem of humanoid robot using a recursive approach. This methodology offers the advantage of reducing the computational complexity associated with dynamic model of the robot. It can be extended to other bipedal robots. The skew-symmetric matrix properties allow for efficient recursive computation of the robot's dynamic model. It has significant relevance in computational applications, as the recursive equation reduces the computational cost of modeling humanoid robots.